right, calculus. I had a couple of questions that people wanted me to go over from page 459. 14B and C and 19B were the questions that I had. So 14, and I may have to do this stuff just before it in order to figure it out, I don't know. But number 14B and C, the Public Works Department of a town counted 400 rats in 1 year. Actually, Moncton's got a huge rat problem, did you know? Anyway, that's just an aside. 400 rats in 1 year. It is predicted that the rat population will grow exponentially for the next few years. If T is the time in years, then the growth constant for the rat population is estimated to be 0.018. So write an equation for this. So the population would be equal to the original population, e to the k times t. So all we're going to do is fill in what we know. And they said the first count that they did, so the original population would be 400. And they said that the growth constant is 0.018 to the t. So that really is just the formula that they want in A. For B, how long will it take, so I'm looking for time, how long will it take for the population to double? So for B, if the population doubles, that means the final population is going to be 800 is equal to 400 e to the 0.018t. So I just divide both sides by 400, so I would have 2 is equal to e to the 0.018t. Now, how do I solve with that? It's not asking me for a rate of change, so I don't have to do the derivative of this. What I'm going to do, though, is I'm going to change it into logarithmic form. So log base e of 2 is 0.018t, right? The base of my exponent is the base of my log. The answer is what I'm taking the log of, and my exponent now becomes my answer. Now, if I have log with base e, that is actually the natural logarithm, which is ln. So I have ln 2 is equal to 0.018t. So I'm going to divide this side by 0.018. So I'm going to divide this side by 0.018. So I'm going to do ln 2 divided by 0.018. And I get t is 38.5. And they said t is in years. So I get 38.5. What do they have at the back of the book? Just double checking to be sure. I'm on page 459. 14. Oh my goodness, I can't find it. There's 9. 10, 11, 12, 13, 14. Yep, 38.5 years. I got it. Okay, and then for the other half of B, it says how long would it take it to triple? So I do exactly the same thing, except instead of 800, I put 1200 here. So this becomes 3. So this becomes ln 3 divided by 0.018, but it's the same process. C, find the rate of change of the population after 10 years. Find the rate of change after 10 years. So we know that P, this is for part C, we know that population is equal to 400 e to the 0.018t. They are now talking rate of change, which means I have to find the derivative. So the derivative. Now here's 400. Here's e to the k times t. So here's my f, here's my g. I am going to do the product rule. So g, leave it alone. F prime would be 0. So really that's gone. Plus f, which is 400 g prime. Now remember, to do the derivative of e, first do the derivative of e, which is just e. then do the derivative of the exponent, which would be 0.018. So to clean this up, my rate of change, first off, that's gone. If I do 400 times 0.018, I get 7.2 e to the 0.018 t. So that's the derivative. That is the rate of change formula. Now they want to know, find the rate of change after 10 years. So I'm going to put 10 in for my time. So I'm going to do 0.018 times 10. I'm going to do e to that number. Whoops. E to the 0.18. And I'm going to multiply by 7.2. And I get that the rate of change after 10 years is 8.62. What that means is that at the 10-year mark, the amount of rats is increasing by almost 9 rats per year. Okay, so 9 rats per year, that's how many it's increasing by. I have a feeling rats would increase faster than that, but anyway. So then if they said 25 years, I'd just put 25 in here, and I would do the same thing. 19, they give you, for 19, they give you the value of dollars of a machine. The value is 50,000. So that means the original price must have been 50,000. E to the negative 0.4. Now the reason why that K, why that growth constant is a negative is because the value of it is depreciating, right? Like when you buy something, 99% of things go down in value when you buy them. Times T, and T is measured in years, and this applies for 10 years. So the person asked me for B, what is the rate of change of the value after 5 years and 10 years? So again, when you see rate of change, think derivative. So again, here would be F, here would be G. So G, F prime plus F, G prime. So the derivative of E is just E, and the derivative of negative 0.4t is negative 0.4. So that's gone because that's times 0. So 50,000 times negative 0.4 is negative 20,000 e to the negative 0.4t. So that is my rate of change, or my derivative formula. They want to know what is the rate of change after 5 years. So I'm going to put 5 in for my time. So negative 0.4 times 5. And I'm going to do e to that. And I'm going to multiply it by negative 20,000. It's going to be negative 2,706.7. Now again, that doesn't mean that the value of this thing, whatever it is, I didn't even look at what it was, it just says of a machine. It doesn't mean that the value of the machine is $2,706. Because it was, remember when you bought it, it was $50,000. I hope in 5 years it's not worth only $2,700. What it means is after 5 years, at the 5th year, it will go down in value by $2,706.70. Okay, so if at the beginning of the 5th year it was worth $40,000, at the end of the 5th year, it would be worth 40,000 minus this. All right? And again, 10 years, you would do the same thing, just put 10 in for that. All right, I want to head into the next section, section 7.7, where we talk about doing derivatives of logarithms. the only way that you can really do derivatives of logarithms is with ease and natural logarithms. So I'm on page 463, and it says, earlier in this chapter we worked with logarithmic functions. Hey, we just finished doing that. Now we're going to find the derivatives of these functions. So we start with the simplest derivative, and that is y is equal to ln x. We're going to talk about how do we find the derivative of that. I'm going to show you how they come up with it, and then I'm going to give you the shortcut. All right? But I want you to see why it is. So first, what we're going to do is we're going to rewrite this as in exponential form instead of logarithmic form. Okay, so ln, remember, is really log base e of x. So if I were to write this in exponential form instead of logarithmic form, what I would do is my base in my log is my base in my exponent. This becomes my exponent, and this becomes my answer. So all I've done is change it from logarithmic form into exponential form. That's all I've done. All right, you're not going to have to do that. I'm doing this to show you how do they come up with the derivative for ln x. All right, now what I would do with that, because I have an x and a y, but my y is in an exponent, I would actually do implicit differentiation. So what that means is I would do the derivative of both sides. But if I'm going to do the derivative of this side, the derivative of e is just e, and I leave this alone. The derivative of y is 1, but remember, when I'm doing the derivative of y, I have to say I did the derivative of y with respect to x. And that is equal to the derivative of x, which is just 1. All right, remember, what we're going to try and do is we're going to try and get the dy dx by itself. So dy dx would actually equal 1 over e to the y, because I'm going to divide this side by e to the y so that they cancel. So I'm going to divide that side by e to the y. So I have dy dx is equal to 1 over e to the y. But I want you to look up here at a statement that I had. I had e to the y is x. So if I have an e to the y, actually I can replace it with an x. So the derivative of ln x is actually 1 over x. So let me explain how this shortcut will work. What we now know is the simplest derivative, ln of x. The simplest derivative is 1 over whatever was here, which is 1 over x. All right? So what if we had ln of 3x squared? Okay. The derivative of that is actually 1 over 3x squared, but there's a second part to it that you don't see when you do this, because notice there's a 1 here. Technically, there's a 1 here because 1 was the derivative of x. So it's really 1 over x times that 1 because it was the derivative of this. So what I actually have to have is, what is the derivative of 3x squared, which would be 6x. So how do I, again, shortcut, how do I shorten this? I think of it this way. First I do the derivative of ln, which is 1 over whatever I'm taking the ln of. So 1 over 3x squared. Then I have to take the derivative of the 3x squared, which is 6x. Now I can shorten that. Okay, I can shorten that because this would actually be 6x over 3x squared. 6 over 3 would actually be 2, and x over x squared would leave you with an x over here. So actually the derivative of ln 3x squared is actually 2 over x. All right? So that really is the shortcut. So we're going to look at example number 1. I'm going to talk you through this several times. So example 1a gives you y is equal to 2 to the x. Now, how do I do a derivative when the x is in an exponent? So again, there are steps that you're going to take every single time. All right, those steps are written halfway down page 464, but here's step 1. Take the ln, because we know how to do the derivative of a ln now, I just showed you. So take the ln of both sides. This is very similar to when we were trying to solve when we had an x in an exponent way back in grade 12. When we were trying to solve for x, we took the log of both sides. When we're trying to do the derivative, we take the ln of both sides. So I'm going to do ln y equals ln of 2 to the x. Now, step number 2, use your power rule. So if you forget what the power rule was, the power rule said if you have an exponent, you can actually move it down in front, okay? Again, this is a logarithm, so it's legal. So you can actually just bring the x down in front. That's what the power rule says you can do. So ln y equals x ln 2. And now we're going to number 3, take the derivative of both sides. Now this can get tricky. All right, so try and follow me through this. Okay. On this side we have ln y. We have to take the derivative of that. So the derivative of ln is 1 over whatever I'm taking the ln of. So in this case it would be 1 over y. Then I have to take the derivative of the y itself, which would be 1. But because it's y, I have to say, listen, when I took that derivative of y, I did it with respect to x. So that is the derivative of this side. Now I can clean that up. 1 over y times 1 is just 1 over y times dy over dx. On this side, I have x times ln of 2. So this is f, this is g. I'm going to have to do the product rule here. I'm going to show you a shortcut. So good news there. So I have to do g, which is ln 2, times f prime. Well, the derivative of x would just be 1, plus f, which is x. Now watch what happens here, because this is important. When I do the derivative of g, the derivative of ln is 1 over whatever I'm taking the ln of. So that would be 1 over 2. But then I have to take the derivative of 2. The derivative of a constant is always 0. So it's just going to work out to be 0 anyway. So here's just a quick shortcut for you. If you were trying to take the derivative of ln of a constant, it's just going to work out to be 0. So the derivative of this, 0. Just like the derivative of a constant is 0, the derivative of ln of a constant is also just 0. So you don't have to do like this, it's 1 over 2 times it. You don't have to do that every time. You can just put 0 in there. So x times a half times 0, that's all just 0, so that's gone. So on this side, I really just have ln 2 times 1, which is just ln 2. So I have 1 over y dy dx is equal to ln 2. Now I want the dy dx by itself, so I'm going to multiply this side by y so it cancels. So I'm going to multiply this side by y. So I have dy dx is equal to ln 2 times y. But up here I have y is 2 to the x. So I can actually just replace that with 2 to the x. So dy over dx is ln 2 times 2 to the x. Now I tend to put brackets around because it's ln 2 times 2 to the x. It's not ln of 2 times 2 to the x. It is not ln of 2 times 2 to the x. Like, that's not right. It's ln 2 times 2 to the x. And that's an important distinction, okay? That is a very different thing. Okay, so 1b, 1b is y is equal to log 3 of x. Okay. For this one, because of the form it's in, because it's got a log in it, and we really don't know how to do the derivative of logs other than a natural logarithm, a ln, but log itself, there's not really an easy way to do a derivative of those. And because it's just log 3 of x, it's really simple. I would change this into exponential form. You really need to be able to go back and forth from one to the other. When I said in grade 12, you need to know how to do that, I wasn't kidding. Okay, so, because I knew this stuff was coming. So the base of my log becomes the base of my exponent. This becomes my exponent, and this becomes my answer. Now I can do these 3 steps in order to do the derivative. Take the ln of both sides. Ln of 3 to the y is equal to ln of x. Okay? Then I can use my power rule. I'm going to bring this y down in front. I have y times ln of 3 is equal to ln of x. Now I can take the derivative of both sides. This side, here's your f, here's your g. You're actually going to do the product rule. So g, which is ln 3, f prime. Well, the derivative of y is 1, but I have to say I did that with respect to x. Plus f, which is y, times g prime. But remember, the derivative of ln 3, since it's a constant, the derivative is just automatically 0. The other side, the derivative of ln x. Well, the derivative of ln is 1 over whatever I'm taking the ln of, and then the derivative of x would just be 1. So, I need space. If I'm cleaning that up, that's gone. I really have ln 3 dy dx equals 1 over x. So dy dx, I'm going to divide this side by ln 3, so I'm going to divide the other side by ln 3, so it really just goes on the bottom here. So I have 1 over x times ln of 3. And that's my derivative. I can't do anything else with that. All right. I'm going to do, let me just look at how long this video is. I'm not even sure yet. It's 24 minutes. I really would like to get this stuff done. So let's do example 2. Page 465, example 2a, there's an A, a B, and a C, is y is equal to x ln x, and they want you to just take the derivative. So in this one, everything is already in a form that's good. It's got a ln x, it just y's and x's, nothing's in exponents or logs or anything like other than ln, so it's all good. So if I'm gonna do the derivative of this, I have two pieces, I'm just going to do the product rule. So g f prime plus f g prime. Now again, the derivative of ln x would be 1 over x times 1. Ln is 1 over x, the derivative of x is just 1. So these x's cancel, I have 1 times 1, so I really have ln x plus 1. So the derivative is just ln x plus 1, and that's it. That one was easy. B, y is log x to the 8th plus 1. So this time I have a log. That's never good. I need lns, not logs. So what I'm going to do with this is I'm going to change this into exponential form. If there's no base on your log, remember, assume it's a 10. So this would be 10 to the y equals x to the 8th plus 1. I have just changed it. Take the ln of both sides. So I'm taking ln of that whole thing, x to the 8th plus 1. Use your power rule. Bring your y down in front. Y times ln 10 is equal to ln of x to the 8th plus 1. On this side, to do the derivative, I'm going to have to use the product rule. So g f prime. So the derivative of y is 1, but I have to say I did the derivative of y with respect to x, plus f, which is y, derivative of ln 10. Again, that's a constant. 10 is a constant, so the derivative is automatically just 0. That's equal to, all right, so over here, the derivative of ln is 1 over whatever I'm taking the ln of, which is x to the 8th plus 1. Then I have to take the derivative of x to the 8th plus 1. Well, I'd bring the 8 down in front. I would have 8x to the 7th, and the derivative of 1 is nothing, so I just have 8x to the 7th. So let's clean this up a little bit. That's gone. I have ln 10 dy dx is equal to 8x to the 7th over x to the 8th plus 1. Side note, you cannot cancel these x's because this is a whole unit, x to the 8th plus 1. The only way I could cancel it with anything on top is if on top I had an x to the 8th plus 1. Then I could cancel it, but I can't because this is part of an addition. I cannot cancel these x's, although some of you would probably want to try. Don't do it, okay? So here's what I have. So I need to divide this side by ln 10. So I'm going to divide this side by ln 10. And so my derivative, my dy over dx, is 8x to the 7th over x to the 8th plus 1 times ln 10. Looks confusing? Yep, but that is the derivative. Last one for example 2. 3 to the y is equal to x squared plus 1. So no logs to get rid of. So I'm going to just start with step 1. Take the ln of both sides. So again, I'm taking the ln of that whole thing, x squared plus 1. Use your power rule. So move your y down in front. So I have y ln 3 is equal to ln of x squared plus 1. This is going to be an awful lot like the one I just did now. Take the derivative of both sides. So this side I'm going to have to do the product rule with. So g f prime, so 1 times dy over dx plus f g prime, but the derivative of ln 3 would be 0. That's equal to, the derivative of ln is 1 over whatever I'm taking the ln of, and then I do the derivative of x squared plus 1, which would just be 2x. So to clean this up, That's gone. I have ln 3 dy over dx equals 2x over x squared plus 1. Again, no canceling those x's, don't try it. So I'm going to divide this side by ln 3. So I'm going to divide this side also by ln 3. And there is my answer. Voila. One more example. Nah, I'm going to do that tomorrow. It's a word problem. I'm actually going to put it in with section 7.8, which is all word problems. I'm going to put that all together. All right, that's it. That's all we're going to do. That's a lot. And I will give you some of those to try. We only have one more section after this for chapter 7. Then we're going to do a couple of sections in chapter 8 and we'll be done. All right, talk to you again soon.